start today's lecture. So I'm going to share my presentation. Right, so I would assume that all of you can see my presentation. So in case if you can't see it, then please let me know. You should see the chapter 1 of my presentation, which is the introduction part. And yesterday I kind of gave you a brush up or a touch up in different from different areas in your lecture note or different areas that we are going to talk. But today I will start from chapter 1. So in this chapter I am going to talk basically about what is astronomy and give an introduction about astronomy and um, maybe a few slides about why you are learning it. Is there like any use of learning it for in astronomy? And then different places that you can apply the knowledge that you take from the astronomy, and then a bit of history or historical event, how the astronomy has developed up to the point where we are now as a subject or as a science, astronomy as a science, how it is developed. So let me, right. Now, the one question before I define anything about astronomy, I mean, why would you learn astronomy? I mean, if somebody asks from you that you are taking this course, and I mean, why do you even take this course? Is there any like specific reason for taking this course, or is this because you just have to take it? This is in your syllabus and you are taking this course. So if somebody asks you, you should have an answer, right? One thing is obvious, like every one of us are so curious that we would like to know about the place that we live, right? So what kind of place that we are living? Are there aliens in are there other planets that we can live? And are there aliens exist? Those kind of questions, right? Um, so these are the questions normally one would be interested and always curious about. And every kid and everyone, when there is an astronomical event, everyone is like interested and curious uh, to look at these objects, right? And right, so now one, and apart from those things, actually the technology that we use right now for our day-to-day life, most of these technologies actually have developed initially in the field of astronomy, astrophysics, cosmology, and particle physics. I mean, this subject seems to be that there is no use for day-to-day life, but the real situation is they are actually pioneers of developing these modern technologies, which they would use for different applications uh, in astronomy, astrophysics, and cosmology. But these technologies are later used by humans for other purposes, right? So that's why I have mentioned here that the benefits of astronomy comes by transferring technology that was originally invented for astronomy. So this is one of the major areas in science that these new technologies emerge and later they are transferred into different fields. And one such example is in the medicine. You probably have heard this the CT scan, right? Which is one of the popular machines that you use for scanning purposes in medicine. And these CT scans are actually initially, so they are using this method called aperture synthesis. This is initially used in the field of astronomy. And in the same way, if you look at the another reason that we are more interested about this field about astronomy and astrophysics is that now we have sun at the center of our solar system, right? Now, our climate is greatly depends on sun. For example, uh, the sun is the main reason uh, that we have different climate patterns that exist in the universe. And also, these asteroids. So asteroids are always a threat in some sense to the universe or to our uh, itself, because there is always a threat that uh, we would be hit by an asteroid that we don't know. And asteroid 211 MD was the latest one that had a very close approach. And maybe there are other asteroids after this as well. And one such event that has happened in the past was this extinction of dinosaurs that you probably have heard. That the story is that what we know right now is the reason for the extinction of these dinosaurs is due to an asteroid, right? So studying space and astronomy actually plays a major part to detect these harmful asteroids and then act on time. So this is like a disaster management in one sense. And the other fields that use the technology that has developed in astronomy, one of the very popular one is actually the Kodak technical pan, and this was actually uh, first used in solar astronomy to record the changes on the surface structure of the sun. Right. This is actually a film. I mean, I don't know whether you have seen this. So when we were like in our childhoods, the cameras we had were not digital cameras. They have this a small film that you have to put into the camera, and then you take pictures and you take out the film, and then you have to go to one of these the shops that they take out all these photos, and these are like printed photos. Like you can't like directly get the images like you now have the opportunity or the chance using your smartphone, right? Now these technologies are actually first used by astronomers because the technologies behind all these cameras, for example, even in DSLR cameras, the chips that they are using, so these technologies are first used by astronomers. uh, we used to tell that these CCD images or charge coupled devices first used by in astronomy. And the reason is that this CCD technology is these chips are the chips that have very less noise and very efficient over a range of wavelengths. So they have a high quantum efficiency and so and so. Because of that, people, astronomers, used to make their cameras that take pictures from these telescopes using these CCD chips. So they first used those, and then later these CCD chips were used for different other purposes such as photography and those kind of things. So that's in the industry. And in terms of the softwares or in the field of computer science, now this language called interactive data language or IDL, this language is first used for data analysis purposes in astronomy. Now it is actually used by General Motors, which is one of these company who made different things to analyze data from car crashes, right? So you can see that these different techniques that technology is developed in astronomy later used for industrial purposes. And another example is iGraph, which we called as, the long name is Image Reduction Analysis Facility. And this is actually collections of softwares written by National Optical Astronomy Observatory. And the purpose of the software is actually to, once you take these CCD images from the telescopes, you need to reduce this image, or what we call this as calibration of images, to use uh, the images for scientific purposes. And then you have to do something called bias subtraction, and then dark frame subtraction, those kind of things. And then there are two processes called astrometry and photometry for these images. I'm not going to talk these things into too much, because that is a separate field called observational astronomy, which we will not touch that much here. And so this is the purpose of this software. But later, this particular software is actually used by AT&T, and I hope that you know about this company. AT&T is one of the famous mobile companies in USA, who used to introduce these mobile technologies, and they used IREF to develop their technologies later. So which means at that time, if there are people who did like astronomy and have used these softwares, they had like good opportunities. If they decide to deviate from astronomy, they used to go and work in these companies, because they have the necessary technology and the knowledge, right? So apart from that, uh, in terms of in the field of communication, the radio astronomy has given birth to great communication tools. So radio astronomy is the separate field in astronomy that you use radio wavelengths to analyze different things or objects in the space. So they have this special program called Fourth programming language, that is again developed by Kitt telescopes and later used by a company to make tracking systems in FedEx. So I don't know whether you know FedEx. FedEx is a courier service that runs all over the world. It is something similar, but in the large scale to the courier services that we have in Sri Lanka, such as Pronto and those kind of things. And also the GPS satellites, they also rely on quasars to determine accurate positions. Now, one interesting thing that I want to mention here is about the general theory of relativity. Now, according to the general theory of relativity, we will briefly learn about these things later as well. There is something called gravitational time dilation. That means when you have large masses, then there is always a time dilation involved in that. Now, when you have these satellites actually placed in orbits, and your Google Map always work with those satellites, right? So they instantly take your position, and then it can accurately predict where you are, right? Just giving these GPS coordinates. But do you know that there should be a correction that you have to apply due to this general theory of relativity of Einstein, which we called as the time dilation or gravitational time dilation. If you did not apply that particular part into these into the calculations of these GPS satellites, your position will be off by a large distance, maybe a few miles. I can't remember the number, but we will talk this about again when it comes to the last section of this lecture series about cosmology. Then I will explain exact amount of difference of these positions if you don't take into account the theory of general relativity. Right, so that's another application. Right, so this is something extra, actually not related to your field of what we call as field of astronomy. This was actually one of the question that I copied from one of these websites called Quora. There was a question that asked, I mean, this is just just a hint for you. If there are, I know that there are always some students who are interested in astronomy. And at the same time, they have this question like what they can do after doing astronomy, right? I mean, if it is just for looking at the sky, then I mean, how you can make a living out of that, right? So that's one of the questions even I had when I was starting this career in astronomy and astrophysics. Now, the question that have posted is it worth to study astronomy, astrophysics if you are not going into academic agencies like NASA, right? I mean, the question is asking, I mean, only these are the two places that we know. When you study astronomy or astrophysics, one would think that maybe you have to end up as a university lecturer or professor, maybe you have to go to NASA, right? So those are the only two things that you know, and these are the things actually I knew when I was starting my PhD as well. But the truth is, the skills that you develop, it is true that you are passionate about looking at these objects and passionate and curious about the universe, and that's why you are studying astronomy. But at the same time, if you like go ahead and do further studies in astronomy and astrophysics, there are certain set of skills that you have to uh, acquire or understand or develop. And from those skills, what would happen is you will use these set of skills in different fields, right? So that's what this answer actually explains, which is most of these people who actually do PhDs or postgraduates in astronomy and astrophysics, they would not end up in in an academic position in the university. So what most of them actually will develop certain skills such as computer programming language knowledge. And then also in the modern days, most of the astronomers have these skills with working a large amount of data, right? And because of that, some of them are actually moving out to data science field. So that's why in this answer, it has mentioned here, like some of them actually went to this field called data science, which you know that one of the like demanding fields of study now. And this is actually one field that you can look into when you are studying astronomy and astrophysics, especially if you are working with large data sets, which means you get this knowledge about handling programming languages such as Python, R, and then working with data with different data science packages so that you will acquire all these knowledge that you need. So it just read through this answer. I will post these slides in your classroom so that you can go through that. And more details are in the internet as well. And this is just to give you an introduction, like where would you use the skills that you develop in astronomy in other fields, right? If you are not, if you will not end up as an astronomer or professional, like in academic body or something like that. I mean, other than just enjoying yourself looking at the sky, right? So that's the initial part. And now let me start uh, talk about astronomy. Now, in terms, so if I need to give a definition for astronomy in different books, it is defined in a few different ways. And one definition would be the study of objects that lie beyond our planet, Earth, and the process by which these objects interact with one another. Now, this is what we do normally in astronomy. We look at the objects outside our planet, right? Everything, all the other research that you are doing is focused to the things inside our planet, and astronomy is in fact the only field that looking at the objects outside our planets, astronomy and astrophysics. And then we look at these objects and then we see how they interact each other, right? So that's how we can define astronomy. And another way that I can explain this is that as an attempt to organize what we learned into clear the history of the universe. So we have a certain set of knowledge and laws, even in physics and in other sciences, and we are trying to apply that knowledge to clear up the history of the universe, starting from the Big Bang up to the present mode. So the Big Bang is the standard theory that we know right now to explain the beginning of the universe. So we use all the physics laws to explain and clear up our path from the past up to the present. The past means starting from the Big Bang up to the present. Now, the important thing here is the physics laws, they don't change from place to place, right? So all the physics laws can be applicable to anywhere in the universe in general. I mean, there are exceptions, but in general, you can apply it. And because of that, we will use those laws to explain uh, different phenomena that happens in the universe, and this will clear up our path starting in the Big Bang up to today. So that's what happens. And at the same time, our universe evolves, right? Even though we try to explain it over a very long period of time, it keeps changing, right? Now, as an example, think about yourself. Initially, at the start of the universe, there were no human being, but once the universe made up with carbon, calcium, and oxygen, so they are necessary element to construct uh, a human being, which is actually a very complicated entity, right? So see the beauty of this science, that at the end you get, starting from the Big Bang, you develop different things, and at the end there is a time that human beings are here, right? And human beings are made of these elements such as calcium, oxygen, those kind of things. And during the lessons that we will learn in the future, you will learn that how these elements came into our universe, right? Especially from the process of star formation, right? Now, actually looking at this evolutionary process or tracing the evolutionary process is also a big part of our modern astronomy as well, right? Now, if I go back to the history of astronomy, initially, actually, the subject of astronomy began with the study of the night sky many thousand years ago in the past. So people looked at the sky, and then after that, I mean, over the past few thousand years, starting from just looking at or observing the night sky, now this branch of science has now uh, involved. Sorry, this branch is now evolved as a modern science. So what astronomers basically do is they will try to observe the universe, and they will attempt to describe it and understand it. Now, this is where the astrophysics comes into play. So once you observe something, then you have to explain it, how it works, right? Now that's what we used to do, and maybe you have been doing this over 3 years in your studies in the universe. Try to learn different theories that are useful to explain uh, how things works. And astronomers actually do the same thing. So they observe the universe, and then they are trying to or attempt to describe those observations and understand it, right? So this is where actually most of the time this the field of astronomy and astrophysics combine together, and why the physics is related to astronomy, because when you have to do the explanations how things works, then you have to incorporate these different theories such as relativity, and then different conservation laws, conservation of momentum, and conservation of energy, those kind of things, right? So those are the applications. And actually, during this process, we have now made a great progress, And the progress is what you have probably seen in my last lecture, very new discoveries and very new explanations. And we have now even have been able to grab a good handle or good idea about black holes as well. But still there are many questions to answer that we don't know. Now, during the lectures throughout this month, we will try to answer these questions, right? Not the questions that is unanswered, but the questions that we can answer, and already we know some of these answers, right? And this is one thing actually that we are still trying to find an answer. And this chart shows different things or different constitutions in the universe. And you can see that ordinary matter means the electrons, protons, and neutrons, and atoms, those kind of matter that we know, is only consist of 4.9 or approximately 5% of the universe. So which means the things that are more familiar to us and things that we know pretty much everything is about these atoms, right? But it's only constitute of 5% of the universe. So which means 95% of the things actually we are still not sure. Now rest of the things is divided into two components. One is called dark matter and the other part is called dark energy. Now both are dark, right? I mean, what's the difference between dark matter and dark energy? Because you know that from the Einstein's equation, you can convert one to another, right? Matter can be converted to energy, energy can be converted to matter. So why do I have two sections like dark matter and dark energy? Does anybody knows what these two means? Right. So actually, these two are, even though the name suggests as dark matter and dark energy, you will learn that in your cosmology lecture that our universe is expanding and at the same time accelerate, right? And dark matter is a matter that inside galaxies or galaxy clusters that are not visible, but they should be there to account for the gravitational effects that we have, right? So then, but we can't see those, right? The normal matter you can see it, right? But for this kind of matter you cannot see it, and because of that we used to tell that those as dark matter. And dark energy is a different story. We know that our universe is now accelerating. It is expanding according to Hubble's law, but at the same time it is accelerating. Now this acceleration is caused by different constitution that we don't know, and that is what we call as dark energy. So that's the difference between dark matter and dark energy. Right. So let me so that is something that actually we don't know. Right. So here are some questions actually we can address in the astronomy course. And in fact, this is what we will do, right? This is like in another way, this will be your syllabus or learning outcomes or some whatever you call this. Is that you, so our aim is to learn the subject and answer these questions at the end. So that's what we are going to do. So during the lectures or after the lectures, once you understand the subject, you should have a better idea about how to answer these questions, right? These questions are not specific, so they are like in broad. I have write it in a broader way, but we will go into each section and then look at what we know about these things. Now, the first thing is, how old is the Earth? the sun and the universe. Anybody knows the age of the universe now? How old is our universe? Is it 1,000 years, 2,000, 5,000?
Sir, around 13 billion years.
Yes. So yes, thank you. And so that is around 13 billion years. By the way, what's your name?
My name is Shodami.
Shodami. Okay. So Shodami, thank you for the answer. So that's correct. And I got another answer from somebody else. So that is 30, it says 13.5 billion years. So roughly it's 13.6 billion years. And the exact value, or the most accurate value, came from the Planck satellite probably a few years ago, and we will discuss about that as well. And for the sun, uh, anybody knows the age of the sun? How old is that? Our own sun. Sun is actually around 5 billion years. Uh, what do you think? Will sun last for another few billion years, or will it? I mean, how long will it last? So that should be an important question for us, right? Because we should know how long the sun would last. Because once the sun is gone, we all of us will be gone, right? So one thing that we need to make sure is that we have to make sure that sun will be there during our lifetime, right? Because if the sun goes, then we all will be gone, right? So in that question, you can understand that how important the subject, this subject, right? Talking about these outer planets. It is true that we give the priority to talk about all these things that seems to be very applicable in terms of the technology wise, but uh, the one thing that we have to make sure before everything is that we need to make sure that our sun is there for a good amount of time, right? Because if the sun is gone, there is no use of doing everything else. Because sun is the main power source for us, and it produces everything that we need, right? So you will probably I will try to give a calculation and show you that the sun will last for another 5 billion years, right? So totally it will be 10 billion years. Because sun is a star, it has a lifetime, and during different places at its life, it will do different things, right? I mean, you will do different things at different times, right? So you went to school for like 13 years, and then went to the, now you are at the some goes into the university, and some went to a different path depending on your A-level results, and then after your undergraduates, you will go for different places. And this is what happened to stars. So the sun is one of those stars. So if stars will go through the whole life story, and depending on the different conditions, the stars will select different paths during their lifetimes. And this is a very, very nice story that we will learn in probably uh, one third of your lectures. Will be going to learn about different evolution patterns and different stages of these stars. So we will use our knowledge in physics, uh, and then uh, basically knowledge in physics that we will use to look at this evolutionary process. And then the stars shine. Even if you go outside right now, you will see stars are shining. And as I told you the last time at the end of the lecture, this time of the year will be probably the best time of the year to look at the sky. And sometimes you will see crystal clear skies, that you see a lot of stars. And you should have this question, why stars shine, right? How long they will last? So we will answer these questions during our lectures. And there are some stars that explodes, right? So when the star explodes, there is a specific name for this process. Anybody knows what do you call for exploding stars? So these are the one actually that we called as supernovas, right? And then we have this question for now hundreds of years now. Do black holes exist? Because there are all these films and everything made out of black holes. So the question that we have as a subject uh, in terms of science, can we claim that the black holes exist or not? And you probably know the answer now because from the last lecture, but we will talk more about those using Einstein's general relativity and some other theories in physics. So don't be afraid that I will not go through these Einstein equations and all this stuff, right? What I would do is I will just get the equations and simple equations and use those to give you simple explanations as this is an introductory course. And the other one is how big is the universe? Will it last forever? The questions that we need to answer, like whether the universe is expanding forever, whether it will expand and contract at one place and they come down, and all these things depends on actually, once again you have to go for Einstein to explain this, and then there is something called scaling parameter, and depending on that there is another quantity called critical density of the universe, which we will use to look at what will be the fate of the universe in future depending on those critical density values. And then the final question everybody has, is there life elsewhere or are we alone, right? And I mean, is there basically, are there aliens? So that's what we are looking at the end. And this is, I mean, not for me, it's not a that much popular question, but for the media actually this is one of the, like you probably have heard like different stories at different times that the aliens came to even Sri Lanka, right? But at the end they came out to be not true, right? There is no scientific base for those stories. But if you know those kind of stories, please share with us so that we will discuss, right? So this is where we are, our earth. So I'm going to start now to talk about these things, and here are the planets. So there is a section that we will talk about planets, but not that much because you can get this information from the internet. Now, this image just to give you a snapshot to get an idea about the sizes of the planets, right? So the thing that you see in this left hand side with these flames, so that represent our own sun, and you can see that compared to sun is very huge that you can't even take that into this picture completely to compare with the other planets. And then you have the Mercury, Venus, the smallest one right here is the first planet, and then here is the Venus and Mercury, and then you have Earth and the mass, and here is the Jupiter, and here is the Saturn. So these two guys are very famous now, right? Because of this great conjunction about the Jupiter and Saturn. And actually, about the great conjunction, there is a nice story that you can predict from the data uh, when it will happen again, right? There are some nice articles about that. So under the topics about the planets, I will talk about those kind of things, the things that are relatively new and seems interesting. And then you have the other two planets like Uranus and Neptune. And I assume that you all know that the Pluto is no more a planet. It was a planet actually when I was in the school, but International Astronomical Union decided that it shouldn't be a planet for a reason. Uh, so now it is called as a dwarf planet because the new definition for the planet, according to this new definition, the Pluto does not belongs to one of those. So to the definition basically, because of that they have removed the Pluto as one of the main planets, but it is still considered as a dwarf planet, so that is a different category, right? Anybody knows what is this? This is actually one of the famous telescopes that I did not show you in the last week, and this is in fact the Hubble telescope. right? Hubble telescope is like very, very famous all over the world, right? The reason that this became famous is not because it is a very big, because there are larger telescopes than this on our own Earth, right? But the Hubble is very famous because it can get like very deep image and look at billions of years far away. The advantage of Hubble telescope is it is in the space, so it doesn't, the light rays that it detects, so it doesn't get any disturbances, right? So it can take like very clear images because in the space, it is in the space, right? And there is a term actually that we use as professional astronomers, which we called as astronomical seeing. Astronomical seeing means actually you measure that particular value. I will go through those things when it comes time. When the time comes, this seeing value is very small for these space-based telescopes, which will give you very clear images. And there are no cloud distractions, so they can operate 365 days. And this is an explosion of a star, supernova 1987A. And we will talk about this. And this is an image taken by the Hubble Space Telescope, by the way, in 1994. And this is again, these are like few images that is taken by the Hubble telescope. And this image is actually an image of a galaxy cluster. And the this name of the galaxy cluster is Abell 1689. So we will talk about galaxy clusters in one of the chapters. And Abell is the one actually, by the way, first cataloged these galaxy clusters using, he just used the naked eye and then looking at these over densities of galaxies in different places in the sky and then make a nice catalog of these galaxy clusters. So he was the first one to do that. And this image is taken from the Hubble telescope, and you can see how clear this image is. And then there are some artifacts kind of things in this image, right? Here is one right here. You can see arcs in different places. You can see right here. Sorry. There are arcs type of thing, different arcs everywhere in this image. Anybody knows what is this effect? What are these things? These are called what? Okay, so these are actually called as gravitational lensing, right? And this is one of the effects predicted by Albert Einstein from his general theory of relativity. What has happened here is that when you have these huge masses inside galaxy clusters, there are a collection of galaxies, which means an enormous mass even you can't think about, right? And because of these masses, the light get bent, right? So this galaxy cluster acts as a lens for the light behind the cluster, which means the cluster, these galaxies act as like lenses and can bend the light. So these arcs are representing that particular effect, which we called as gravitational lensing. Right. So the question that we had, the age of the universe, right? This is the most accurate age now we know, 13.813 and plus or minus 0.058 billion years. Right? GYRS means the billion years. So keep these numbers in your and units in your mind, right? So these will be important in your exams, right? And what is the relation between this particular image and the age of the universe? And this is the latest map of something called cosmic microwave background, which means the Big Bang has predicted this cosmic microwave background should be all over the universe, which has a temperature close to 3 Kelvin. And at the same time, there are some variations of that temperature. That variation is actually shown in these different colors. The blue colors are low temperature, and this orange type of colors are a bit high temperature. And this Planck satellite has measured all these things, and this can be used to estimate the age of the universe, right? So that's why that is the connection between the number and the picture, basically, right? So those are few things that few extra things again. Now in ancient astronomy has a huge. I mean, if you are trying to look at the history of astronomy, it goes back to thousands of years back, and we can't learn everything about the history of astronomy, right? Then it will be a different course. But I will give you some of the interesting things that how people have used these concepts about stars to their own users, and this is one of those that people in US and maybe in other countries have used. And the image that you see in the right hand side, uh, there is a small. You can see that there is a small circular type thing right here, and this is called medicine wheel. I mean, there is no connection with the medicine. The name is for some reason appear as the medicine wheel. Actually, this medicine wheel has used by these Asian Americans as a calendar or something that they can keep the time or track the time, and this is very helpful for them to uh, decide different seasons and their cultivations according to that, right? For example, depending on the places of different stars, they have made this diagram, and then using the diagram, they can predict that, okay, now the winter is coming depending on the stars that rise and set at different times in the year. And then they change their lifestyles and everything based on that. And this is one of the ancient stories to show that these people, even before the Galileo and Copernicus, that they have used this uh, use the sky and stars to keep or use to do their day-to-day work, right? And this medicine wheel, I guess, still in one of these states in USA. I guess the state should be Colombia or something like that. I can't remember that exactly. And the important thing is this is actually remaining as a remnant that you can still see, right? And after that, so that is just back in very early ages. And then, this Plato, one of these Greek philosophers, so he suggested, now when you look at our own earth, what you can see is just if you go outside at a daytime, you can see that even in the night time, so everything is going around us, going around you, right, on the sky, right? So that's what you see. So this he suggested this geocentric universe to explain the motions of objects in the sky, and which is very very fair thing at that time, because once you go out, you can see everything is moving around you, right, on the sky. So he suggested the geocentric universe. What that means is the Earth is at the center, and everything else is moving around us, including our own sun, right? So that was his uh, assumption or the suggestion, right? Now that was actually the belief for a long time between the among the people, that everything goes around us and we are at the center of the universe, right? But uh, there was an actually problem with this, that is the retrograde motion of the planets such as Mars, right? So what this retrograde motion means is that sometimes you see that instead of going the planet going in a one direction, sometimes it goes to, let's say, uh, a planet rise from the east side and it moves towards the west, and sometimes you see that the planets go in a certain direction and suddenly change the direction and go into backward for some time and then come go forward again, right? And this is called a retrograde motion, right? So make sure that you keep these specific words in your mind, right? Retrograde motion, because you don't, some most of the time you don't need these words in other subjects. And because this retrograde motion became a problem and they could not explain this retrograde motion nearly for 2000 years, because they were thinking that the sun is at the center, our earth is at the center, right? And if the earth is at the center, it is hard to explain this. However, around 150 BC, Hipparchus, one of the astronomers at that time, he proposed a different system uh, to explain this retrograde motion, right? So he also thought that the earth is at the center, and then proposed a set of epicycles. I will show a diagram in the next slide uh, to explain this particular phenomena or the retrograde motion, right? And the epicycle was something like this, and you can see that earth is right here at the center, and he was explaining that instead of planet moving around a circular path like this, there is a circle uh, with respect to the center of this path, which is this one right here. And this particular planet is actually moving on this circle, right? A different circle, which he called as epicycles. You can see that when you keep this second planet, let's say this is mass on this epicycle, then from the Earth, you can easily explain it, because at some point it goes in this direction, and after some time it goes into the next this direction, and again to this direction, right? So you can, if you put this in an epicycle, then you can explain this retrograde motion. So that's why they did it. But later, actually, Copernicus is suggested this heliocentric model that means the sun is in at our center of the solar system, and all the other planets are moving around it. Now, this has actually solved this problem. Now you can see that when you think about sun is at the center, the some of the planets that are far away from us will move slowly, and the planets that are closer to us move faster, right? So which means with respect to one another, so they will have different what do you call this different speed. So you can explain the retrograde motion, right? And there are like number of videos even in the YouTube that explains how retrograde motion works according to this model about the heliocentric, that is the sun-centered model, which is the accepted and the correct model. Now we know about that. And right, so that's a bit of history about the astronomy. So basically one of the main things that the sun-centered universe. And as a science subject, uh, so we believe that the science of astronomy has started from the Greeks' traditional natural philosophy, right? So they are the one, actually, you know, the Greeks are very famous for this mathematics, right? So they are the one that use this language of mathematics to explain different observable universe, right? So they use mathematical concepts and mathematics to explain all these things that they see in the universe. And as you know, as similar to other sciences, astronomers used to make hypotheses and design experiments and collect and analyze the data, right? So that's what we do. The only thing is that when you do something on the Earth, specifically for other subjects, you can touch or you can see it very clearly. Uh, I mean, you can go close to that, but for the for the astronomers, you can't do that, right? All these objects are very far away from us, so that you have to rely on uh, different techniques. So what we do is we now have a good understanding about our universe, and what we are doing is we make observations and take data, and then from this data we take results and see whether these results fit with our current understanding of the universe, right? So that's what we do in astronomy as a science subject, right? And one thing to note here is, remember that astronomy is one thing and the astrology is completely different thing, right? So we don't talk about that here. And as I told you, for the astronomers, they are unable to touch or manipulate objects they study, right? So what we are basically doing is we gather light from these distant objects. And this is why we are using this nice instrument that we called as the telescope, right? So what these telescopes are doing is just gathering light from these distant objects. And depending on the type of telescope, it may gather light, visible light, it may gather radio waves, may gather another light, let's say IR, or maybe some other wavelength range, right? Depending on the telescope. So there are different types of telescopes for different, uh, for different wavelength ranges. We will have a separate section, one lecture about devoted to talk about technologies behind the telescopes and what are the modern telescopes now exist in the universe. And there was a question from one student yesterday about how you can choose a telescope, and I will add some more details into that presentation this time, just to explain a bit more about the smaller telescopes, right? Right. So for the let me just so I will continue until 7:30, but okay, let's move on. Oh, I guess my mic was silent for some time. I don't know how long it was silent, right? I mean, somebody just pointed out, Janit, thank you. And was it for a long time or it just happened now?
Yes,
Because
Maybe around for 5 minutes, sir.
okay, so let me just repeat a bit here then. Thank you for pointing it out. Right, so let me start from here. Maybe when I was explaining you this sky charts, it maybe is muted. I don't know. It's okay. I mean, I can just repeat it tomorrow as well. So what I was explaining is actually I will be uh, dividing my lectures into these four parts, except the first two sections, which I will talk a little bit about the electromagnetic spectrum and the telescopes that we will use, right? And also the naked, I have a different section called naked eye astronomy that I will explain how to look at the sky and those kind of things at the beginning, because those things are needed when you learn uh, astronomy. Except for that, then this will be the main part of my, these are the four sections that I will talk. First section will be about planets, comets, asteroids, and then the second one I will talk about stars, and especially their birth, and then the evolution of the stars, and then what will happen to them at the end. And then I will talk about the large scale structure of the universe, which is about the galaxies, and properties of our own Milky Way and different types of galaxies and their properties, those kind of things. And then the cosmology will be the last part, which is about the origin and the evolution of the universe. So that's what I was actually mentioning very briefly. Right, so before we start anything, we have to get an idea about the units that we are going to use in our lecture. I mean, in the field of astronomy. And as I show you that the objects that we are looking at are very far away compared to the objects on the earth, right? Now, for example, if I am going to measure the distance to the sun from the earth using meters, the one that I have marked here, this is the distance. Now you can see that how hard for me to even read this number, right? Because these are huge numbers and it is hard to keep the records in these units. So we are introducing new set of units to distance measurements in the field of astronomy. It is very, very important that you keep these units in your heart, right? Because I am going to use these units very frequently, and I wouldn't use meters unless I really need to do it, or I have to do a unit conversion, right? So the distances that I will use is now for the first time I'm going to introduce you a unit called astronomical unit. So I am going to use this unit.
Sir, sorry for the interruption. Are you sharing anything? We couldn't see anything, sir.
Surprising. So let me see. Let me just give me a minute. Can you see it now? The
Yes,
presentation?
Yes, sir.
Okay, thank you. So sorry about that. Maybe something has happened here. Okay, so actually I was sharing this. Um, so as you see here, what I was mentioning is that this is the distance from Earth to the sun, which is a very, very large number that it's hard to keep track on these numbers. Because of that, I am introducing these new set of units. In fact, it is not that I am introducing these are the standard units, and I am introducing to you about these units, and I am going to use these units very frequently from now on, right? So when I need to tell the distance from sun to earth, I will tell that the distance will be 1 astronomical unit, and in fact that is the definition of the astronomical unit, right? You know that when you need to convert meters into kilometers, you convert it by dividing 1000 or kilometers into meters, multiplying by 1000. In the same way, 1 astronomical unit is equal to this much. So this is roughly the distance from sun to earth. So what that means is, in terms of astronomical units, distance from us to the sun will be 1 astronomical unit, right? So that is the exact, that is the unit conversion and also the definition. So if somebody asks you to define the astronomical unit, 1 astronomical unit will be equal to the average distance between the earth and sun. So keep that in your mind, right? So this is, you have to memorize. If you will use it, once you use it, you will get used to it, right? Now this unit, astronomical unit, is actually very useful when we are discussing distances within our solar system, right? Now this indicates another thing, which means we will talk about distances outside our solar system. So when we are doing that, astronomical unit is even not enough. Now for that, we will move on to the next scale, which we call as the light year, right? And in everyday standards, this is actually a very astronomical unit is a very large, because if I tell that a car is moving at 100 kilometers per hour, it would take 170 years to travel a distance of 1 astronomical unit, right? Now this is like making a highway in Sri Lanka to the sun, right? So it will take 170 years even to travel there. So you will not live. But the thing is, the universe is actually, I mean, it is 1 astronomical unit. 170 years means 1 astronomical unit. But at the same time, universe is even a bigger place than that. Now, if you consider the nearest star to the sun, do you know what is the nearest star to the sun? This is Proxima Centauri, right? As far as I remember. Right. And then this Proxima Centauri, the distance in terms of astronomical unit, it is 270,000 astronomical unit, right? So you can see that this unit is also going to be not enough very soon when you go for outer distances such as galactic distances and so and so. So when it comes to these type of distances, we used to use this new unit called light years, right? So when measuring the distances to stars and galaxies, we will use larger unit called light years. And 1 light year is the distance that the light travels in 1 year. That is the definition. And I know that you know about these things. And right, so 1 light year is roughly equal to 9.46 times 10 to the power 12 kilometers. Right. Here are some examples in terms of these distances. The nearest star to the sun is called the Proxima Centauri. So that's what I mentioned here. That is 4.2 light years away. Now see, it is easy to mention these distances in terms of light years, right? And the center of our galaxy is about 26,000 light years away. Now you can see that when you go for these galactic distances, it is increasing now, even in terms of light years, right? Right. The nearest larger galaxy for us is the Andromeda galaxy. So that is 2.5 million light years away. And the most distant galaxies observed are about 13 billion light years away. now you can see that when you go for these extragalactic distances, even the unit light year is sometimes seems to be not enough. But there is another unit that we use, which we called as parsecs. I think I may not have mentioned it here, but I will introduce it when it comes to talk about stars, right? Because for our solar system, we only have the sun as a star, and astronomical unit as is enough. And for the nearest stars, light years is enough. But when we go far beyond that, we will use this unit called parsecs, and there is a definition for that as well. Right. Uh, so what we actually do is actually looking back the time, right? So astronomy is the only branch of science which we can see the universe as it was in the past. Now, this is one of the advantages. I mean, out of all these things that we can't touch these objects and those kind of problems, this is the only branch that that you can look at the past, right? So that automatically comes in because of these enormous distances involved, right? So, for example, when you are looking at light year units, the distances measurement also tell us how far we are looking back in the time. For example, when we see the sun is actually what we are seeing is how it looks like 8 minutes ago. Have you ever thought about this even, right? So what we are actually seeing is what has happened 10 minutes ago. I mean, close to 10 minutes ago for the sun. Now for the other object, it is the same, right? For example, the Proxima Centauri, what we are seeing is how it was 4.2 years ago, right? Now you can see that these distances, when you go outside today and look at this star cluster, which I called as Pleiades or Seven Sisters, what is the distance to that star cluster? This is actually I mean, I can't remember the rough exact number, but roughly this is around 440 light years away from us, right? This is star cluster, which means when if you go outside right now, look at this star cluster, what you are seeing is how it looks like 440 years ago, right? Not how it looks like right now. This is what makes things interesting, right? Right. So that will yes. Now the thing is, the further we out and look at in the universe, what we are doing is we are further back in time, right? So we things that we see are further back in time. So that's the advantage. So people make this bigger and bigger telescopes to look at the thing to further and further back in the time. So that's what astronomers are doing right now, right? So now we can actually look at so far away things like galaxies and galaxy clusters. Now, as an example, that I have this experience looking at galaxy clusters which are around 1,000 million light years away, right? Which means, so when I suddenly come home and look at these images, it came into my mind is that what came into my mind is that what I am looking at is actually how these galaxies and galaxy clusters looks like probably 1,000 million years away, right? Maybe these galaxy clusters are not there anymore. Maybe they have completely destroyed or something has happened. We don't know, because when we look at these right now, what we see is how it looks like maybe millions of years ago, and there is no way that to see how it looks like right now, right? Because it takes time for the light to travel from these distance objects to right up to now. Right, so final few minutes. So this is the end of the first lecture, and this is actually about basic history of the universe and also the units that I am going to use, and just to make you curious about how we are looking back in the time, right, in astronomy. And the next day, I will actually look at the different coordinate systems that we are looking at. that we are using in astronomy. And if time permits, maybe I will look at try to get some details about the naked eye astronomy as well, right? So there are different coordinate systems that we look at, and this will be important for you, the people who are actually trying to look for buying a new telescope, because the coordinate system is something that you have to look at when you buy a telescope, because there are some telescopes that use this altitude azimuth coordinate system, and there are some telescopes that use something called equatorial coordinate systems, and these are a bit different. And I mean, once you have a good idea about the coordinate systems, that will help as well. And also, to observe any object in the universe, you should have a good idea about, especially for the research purpose, you should have a good idea about some of these coordinate systems, how you locate objects and those kind of things. Right. So that's it for today. And once again, I will, the plan is to do another lecture at tomorrow 6. I hope that's okay for you, right? And maybe another lecture on Saturday as well, if that is fine with you. I guess it should be okay, because I have to finish these lectures by the first week of next month. So that's what I was informed. So